flat, flat. Flat ass.
There's no way.
Flat ass. How many of you got that the vector for the first one was the same? How many of you realized that's because that was the tangent vector to the path, and the path was a geodesic, therefore you could have skipped all the work and just said, by the definition of a geodesic is something which parallel transports its own tangent vector. It's okay, I didn't expect anyone to use that reasoning. I just threw that in as a little, what do they call it when there's a special
Well,
thing
I
you can
thought about
discover?
it, and I looked back at my notes, and I don't think you said that it parallel transports back.
Well, no, this was in my definition of a geodesic as a curve which parallel transports its own tangent vector. It doesn't matter.
Yeah.
Okay. Shh. I know you're all very excited about that quiz and about what we're going to learn today, so let's get to it. So just a reminder, in case someone wasn't here last time or you forgot, your midterm is going to be Tuesday. It is going to be totally open everything. You can look at past assignments, past solutions to assignments, quizzes, everything. To get the timing down, since we've got an hour and 15 minutes, I'll probably have you do 5 questions, but I'll probably write 1 from each homework assignment, so there'll be 8 questions and you can pick 5 to do, okay? All right, and you won't have a homework due next Tuesday, obviously. Okay, so I said last time that I was going to end by telling you what general relativity was, and that might have led you to think that I was going to start today by telling you what general relativity was, but I'm not. And that sucks. But in looking at the material, it makes a lot more sense to talk Thursday about general relativity and the subsequent topic, partly because we have a little bit more time. And so today we're going to talk about something which was on the website. That's what I advertised for today. And what I will say about today is that it is very, very useful. It will be a little bit of that sort of deriving things where I'll have to turn around and occasionally wake you up. But we'll be deriving some things. I'll point to the final results where I say, hey, this is really important. And we get to get one of those cool physics names in the story, okay? Because naming things is always cool in physics. So what we're going to talk about today is conserved quantities and space-time symmetries. And space-time symmetries are also sometimes called isometries of the geometry. So I might say the word isometry. And that's what I mean. And I'm using the word conserved here in sort of the colloquial sense where when I say something is conserved, I mean it doesn't change with time. We're a little bit more careful about that in Physics 1 because students get confused. A conserved quantity is technically a quantity where you can explain the change in time due to the flux of some current through a bounding surface. But today we're just going to talk about whether things change in time or not, and I'm going to try and use the word constant, although I might slip and say the word conserved, but I mean the same thing. So I'm going to start with an argument that hopefully you all should have seen, except for those of you who have not taken intermediate mechanics, and it's okay because what we're going to do today doesn't hang on it. But you should have seen from the Euler-Lagrange equations in Lagrangian mechanics the following very simple argument. So the Euler-Lagrange equation says something like this, where this dot is derivative with respect to time. And xi is the ith component of the spatial position, and this, of course, is the ith component of the velocity. So the Euler-Lagrange equation looks like that, and then hopefully at some point this quantity in parentheses should have been defined to you as the conjugate momentum pi. So if you take the partial derivative of the Lagrangian with respect to the velocity component, that defines the conjugate momentum pi. But then what you can do is make a very, very simple conclusion based on this, and that is, if I just rearrange this equation, it looks like that, okay? And Jacob is going to be the proud winner of the opportunity to tell me under what situations we can say that the ith component of the momentum is constant in time?
I never did IMAC.
Well, I've got it written right here for you. So, but if you did, okay, if you did take IMEC, this is really unfair for you. So you get to phone a friend for sure.
I'm not looking at it.
You what?
I'm not looking at it. You can't choose me.
So you're denouncing yourself as his friend?
Yes.
You sit really close to him all the time.
Wait, no, I never announced that I was his friend.
Okay. Wow. Leo, you want to take this one? Okay, so anybody, any takers out there? Under what conditions is the momentum constant? Gabriel.
Or something. Yeah. Or the Lagrangian with respect to.
Thank you. I actually literally want you to read this equation. This is 0 if the Lagrangian is independent of the coordinate xi. That's what I meant for you to do. Okay? So does that make sense? Okay, so the left-hand side is 0 if the right-hand side is 0. It's an equation. That's what it means. So for the momentum to be constant, the momentum is constant. That component of momentum is constant if the Lagrangian doesn't depend on that coordinate. Okay? How many of you have seen that argument in your intermediate mechanics class? Okay, it's a good one. Now this is a very special limited result of a much more powerful theorem due to Nether, who demonstrated that if the Lagrangian has a continuous symmetry, and in this case that continuous symmetry would be translations along x, because if the Lagrangian doesn't depend on x, you can change the value of x and the Lagrangian won't change. But Nether's theorem states that if the Lagrangian has a continuous symmetry, then there is always a conserved current associated with that symmetry. And from that conserved current, you can then, under certain situations, define something which doesn't change with time. We're not going to need to deal with Nether's full theorem. This is just sort of a little example of how symmetries give rise to constant or conserved quantities. And we want to take this story and we want to translate it to what happens in GR. Now, we are not going to do Lagrangian formulations of GR in this class. I would certainly love to fit that in, but there are other cooler things we have to talk about, like black holes and stuff. So when we look for symmetries and conserved or constant quantities, we're going to have to make use of some mechanism aside from Nether's theorem or thinking about Lagrangians in general. So, what are we going to do? So, what we would like to get out of our discussion is some condition that implies that some component of momentum is constant, but of course constant with respect to what? We don't really like to use time in GR because time is just one of the coordinates and you can change t with a transformation. And so we're going to argue that we want the momentum component to be constant with respect to tau, where tau is the length of the invariant interval. That's the thing we use to parameterize paths for massive things. It's the thing we use to define Four velocity, for example. So we would like to find a condition which tells us that some momentum constant is not changing. All right, so here goes the story. So we can start with a sort of a simple limit, well, it's not simple, a limited argument, and then what I'm going to do is at the end of this, I'm going to take it to the next level. All right, so let's start out by just trying to get something on the table. So remember that for momentum is defined as the mass times the Four velocity, and of course the Four velocity is just the derivative of the coordinate position 4 vector with respect to tau. So that is our definition of Four momentum for massive particles. Obviously, this definition does not work for massless particles, and we have other tools at our disposal for massless particles, but I'm just going to talk about massive particles today. Okay, now if we're talking about massive particles, and we're really just focusing on the gravitational part of the story, what equation governs the behavior of massive particles? Kara? Well, you're giving me Newton's law of gravitation, but what I'm thinking more of is I've got some curved geometry and I want to know if I put a massive particle in that geometry, what path will it take? She called you out. The geodesic equation. So remember that's the importance of the geodesic equation. Geodesics are the paths followed by massive particles. They're actually also followed by massless particles, but they're the paths followed by particles in a curved geometry. So if we're going to try and find some condition that talks about when a momentum component is constant, maybe we should start by looking at the geodesic equation. So let us remind ourselves what this looks like. So we can write dx nu d tau del nu dx mu d tau equals 0. That's one way to write it. Of course, you can break up the covariant derivative and then let it act on this vector and then recombine things and relabel things. So we can write it in a couple of different ways, but this is the way I want to start with it today, because you might notice that this term and this term look like part of our definition of momentum. Okay? So I can actually turn this into a statement about before momentum. Just by multiplying both of those derivatives by m, where m is constant. Okay. But secretly, using our definition of the directional derivative, we can also write this as m times the directional derivative of the momentum with respect to the path parameterized by tau. So all of these expressions are basically saying the same thing. We can write things in different ways. Okay, so what we're going to do is we're going to utilize this guy. And the first thing I'm going to do, and of course that's equal to 0, that's the form of the equation I want to use. 0 is equal to p nu del nu p mu. And the first thing I'm going to do is I'm going to hit both sides of this with the factor of the metric to bring this mu down and make it into an alpha. So applying g alpha mu to both sides is going to give me 0. And then p nu g alpha mu del nu p mu. Okay. Now, I've got to be a little bit careful, right? Because that g mu, this story is arbitrary. So we could be on a curved geometry. The metric could be position dependent. All right. This, of course, is a derivative. So we can ask ourselves, is it legitimate to push this thing through the derivative and let it bring down that mu index? And Bree is going to remind us whether or not we're allowed to do that. You got a 50% chance. Unless you say maybe. But like that would give you worse odds. So I would go with either yes or no.
Yes.
Yes, yes, like because we'd be screwed if we couldn't. Does anybody remember where in our analysis of things we made the statement that the metric and the covariant derivative can be interchanged? It was when we were deriving the covariant derivative, and we specified a condition called metric compatibility. I think I've got too many eyes in there. And metric compatibility was just the statement that the covariant derivative of the metric is 0. The metric is covariantly constant. But if it's covariantly constant, you can move it past the derivative. That's what we mean when we say things are constant. Okay? So I am free to slip the g alpha mu past the derivative, and in this case, this just becomes p nu del nu p alpha, using the metric compatibility condition. That's a very, very important, like write that down and put a block around it. It's very important because in GR, there's a lot of things that you could do with the metric in flat space that you normally can't do. Like the metric is a function of stuff. Normally, you got to be careful. The inverse is not equal to the original metric. There's lots of things that change when you're in GR on curved spaces, so make sure you know the rules for what you can and can't do. Okay, so now we're going to take this expression and we're going to blow it up a little bit by actually writing down what the covariant derivative looks like, except the covariant derivative is acting on the dual vector now. Okay, that was basically the point of using this G alpha mu, was to bring this index down so that this is a dual vector. And I'm going to use lambda. Okay. So that is our usual expression for how the covariant derivative acts on a dual vector. You get a minus contribution from the Christoffel connections, and then all the indices just have to sort themselves out. Yes? Okay, good. I like questions like that. Okay, so this first term I can rewrite by reminding myself that this quantity here is m dx nu d tau. Okay? And so the first term I can actually rewrite as m dp alpha d tau. Okay? Because I can take the m dx nu d tau d nu and rewrite that as the directional derivative. Okay? So the expression that we're using is that dx nu d tau d nu is equal to d by d tau. Okay, remember we're using that kind of funny calculus cancellation rule that you're not supposed to really think about, but we do it anyway, where I say, oh, the dx is cancelled, therefore that's just a derivative with respect to tau. But this is the derivative of a quantity along the path parametrized by tau. This is just doing the same thing, but going through the intermediate step of setting up coordinates and using the coordinates to kind of define how things are changing, and then talking about how the coordinates change with respect to the path. Okay? The second term here, I'm going to go through the painful process of actually writing down the definition of the Christoffel connection. So this is going to be, oh dear Lord, it's going to be ugly. That's what it's going to be. Minus p nu, and then the definition of the Christoffel connection, 1/2 g lambda beta, and then this is d nu g alpha beta plus partial alpha g beta nu minus partial beta g nu alpha. So as this expression on the board blows up and gets bigger and nastier, just remember we're just throwing definitions that we've seen before. Many of them we've derived before. We're just throwing those definitions at this expression. And like hopefully you've realized in many of your physics classes, this is not the kind of thing that any reasonable person sits down and derives from cold like the first time. You know, people spent many years working on these ideas, and they finally got this really cool derivation, and then they teach classes and they present it like this was just the God's truth that was written on a stone tablet and handed to them from the top of a mountain. But no, I mean, this is really, it's like magic. The end result's going to be the important part, but you got to see the steps to get there. Okay, so let's take this second term and beat it up a little bit. Yeah. Yes, okay, so I'm going to take the G here, and I'm going to use it to raise that lambda and make it a beta. And I will say, though, that there is some motivation for some of these steps, because as you will discover in relativity, general and special, there's this one thing that people love to use, and we've used it before, and when I get to it, you'll go like, oh yeah, I remember that. Okay, so there's sort of a method to this madness. There's a direction we're going. So the first thing that I'm going to do is take this expression and I'm going to reorder these two indices because this is a metric factor and I'm always free to do that. Okay. And yes. Okay, so then we've got m dp alpha d tau. And then all I'm going to do is I'm going to peel off two of these terms and then leave the third one as the redheaded stepchild. I apologize if any of you are redheaded stepchildren. I find nothing particularly bad about redheaded stepchildren. It's just a saying from where I grew up. But of course, if I used every saying from where I grew up, I would probably be fired. So let's just not go there. I grew up in the suburbs of the south suburbs of Atlanta, Georgia. Don't go there. Figuratively or literally. Okay, now. There's magic in this expression. Chase. Ready? There are largely three terms in this expression. I would argue to you one of them is identically zero. Which one do you think it is?
The middle one.
Why? Yes? And why?
I would argue it's based off the structure of the metric.
Partly. So does anybody remember this really cool trick I showed you where I said if you've got something like this and you fully contract it with something like this, then it's automatically zero?
Mm.
What were those two things?
It was a,
This is symmetric and anti-symmetric.
It's a symmetric and an anti-symmetric combination of indices.
Yeah.
So let's look at this term right here. What do I get if I interchange beta and nu on this term? The same thing. So this is symmetric. What happens if I interchange beta and nu in this expression? You get a minus sign. So the beta and nu here are anti-symmetric. The beta and nu here are symmetric, but the beta and nu here are completely contracted with the beta and nu here. So that whole middle term vanishes. Okay, I'm going to use that argument a couple of times today. Okay. So that's what I was saying, like when people are massaging these expressions and making these steps, and you're like, why in the world are you picking off those two terms? Part of it is because they know they're going to apply this symmetric, anti-symmetric combination. Okay, so at the end of the day, we've got something good because this whole thing is equal to zero. And so that means that I can rewrite this, and I'll just do it up here. Yeah. So I can rewrite this and say that m dp alpha d tau is equal to 1/2 partial alpha g beta nu p nu p beta. Okay? And now we can kind of go through and make one of those statements where we say, well, m is not zero. I'm by definition looking at massive particles. Okay, 1/2 is not zero. If 1/2 was zero, we would have really broken math and physics. And the product of these two momenta have to have at least some non-zero components. So the only way that the left-hand side of this equation could be zero is if dp alpha d tau equals zero. But when is that going to happen? When this factor equals zero. That is, the can I say this? The alpha component of the dual momentum is constant if the metric does not depend on the coordinate x alpha. Sounds a lot like what we said for the Lagrangian. If the Lagrangian doesn't depend on a particular coordinate, then the momentum component associated with that coordinate is constant in time. Okay? So yeah, it took some nasty manipulation of the geodesic equation, but we got to a result which is, at some level, reasonable. It's phrased not in terms of a Lagrangian, but in terms of the metric. But that's sort of the central figure in general relativity. Okay? Any questions about that? All right. Now, unfortunately, as clean as this is, I mean, this equation basically says something which is perfectly analogous to what we said for Lagrangians. As clean as this is, it's not particularly useful. Okay? Because this is a very coordinate-dependent statement. For example, let's look at flat space. You know, in R2, I can have the metric be 1, 0, 0, 1 if I'm working with rectangular coordinates. And then you would say, oh, there's the x component of the dual momentum is constant, and the y component of the dual momentum is constant, because neither of those appear in the metric. Okay? But I could just change coordinates. And if I change coordinates, suddenly I find, oh, wait a minute, the metric depends on r, so the rth component of the dual momentum would not be constant. The theta component would be constant, but not the rth. I love that I'm saying rth. Feels good. I'm gonna enjoy this lecture. Okay, but that kind of seems weird, right? Because it's the same space. Like if you have two conserved momentum components in one coordinate system, you should really have two conserved momentum components in the other. You shouldn't lose the number of conserved quantities. There is another conserved quantity in the polar coordinate description. It's just using this prescription makes it a little obscure. So what we would like to do, and this is taking it to the next level, is find a way to discover constant or conserved quantities that doesn't require particular choice of coordinates. We would like a sort of coordinate-independent way of finding these conserved quantities. Okay? And this is sort of a motivational example for why this tool is not particularly useful. All right? So let's see what we can do that's more general. And I know I'm probably going to end up wishing that I didn't do this, but I just did it because I need the space. So suppose that, and this is going to piss me off. I've got it written with a lower index. Hold on just a second. I'm not sure how crazy. Yeah, okay, I'm gonna try and transcribe this. Okay, suppose that P sigma star is a constant momentum component, i.e. dp sigma star d tau equals 0. Okay, and the sigma star notation, first of all, it's Carroll's choice, so if you read the book, this is what he chooses. The star is just to remind you that this is not a whole momentum vector. If I wrote P sigma, that would be a 4-component vector. The star is just saying it's one particular component of that vector. Okay. So for example, this is not a tensor equation because P sigma star is a component of the vector. Okay. Okay, now what we're going to do is introduce a vector k mu such that if I contract k mu with an arbitrary dual momentum p lower mu, so what I have in mind is I've got maybe a massive particle, and it's got some 4 momentum, which I can dualize to make the index lower. Okay, I've got this 4 momentum, and I'm ultimately interested in finding a condition where one of the components of that 4 momentum is constant. Okay, so I want to define a vector k mu such that this combination, which by the way is automatically equal to that combination, I can write it either way, where this combination is the quantity p sigma star. Okay? So taking this particular vector, contracting it with this vector, is just going to grab one of the components. So let me give you an example of what that might look like. Okay, so p mu, here I'll do it this way, p upper mu might have components p0, p1, p2, p3, okay? And in this story, maybe it turns out that p2 is constant. Okay? What would k mu be? I want k mu, p mu to give me back the one that's constant, which is p2. Mike?
0, 0, 1, 0.
Yeah, this would just be 0, 0, 1, 0. That's all we're doing. I'm not telling you up front which component it is or what the form of this vector is. That's the power of this. It's very general. But this is just a toy example to show you what I mean when I say k mu, p mu is going to give me the component that's constant. Okay? All right. Now what we can say is, if dp sigma star d tau equals 0, then of course d k mu p mu d tau equals 0, because k mu p mu is defined to be the p sigma star component. Right? And now we're going to play the same game that we played on the previous derivation. We're going to break this up. So this is the directional derivative of this quantity, which I can, of course, break up using a coordinate description. Okay? Kate. Can I use the partial here, or do I need to use the covariant derivative?
I think partial is fine because you only have vectors and dual vectors.
The partial is fine because I only have vectors and dual vectors?
Yeah. That's what I would say. I don't know.
When are we allowed to replace the covariant derivative with the ordinary derivative?
When it is a constant, which,
Uh,
or when you're taking the derivative of a constant, or?
Not a well, you're using the word constant as a
Or
proxy.
scalar.
Scalar, yes. The derivative on a scalar, you can use the ordinary or the covariant, it doesn't matter. But this is exactly a scalar, and this might have been what you were alluding to, that it has a vector and a dual vector index, but they're contracted. But that means that I could, if I wanted to, replace this with the covariant derivative, which is what I have to do if I want to apply the Leibniz rule. If I actually want to take the derivative of these terms in sort of a product rule fashion, because then I am taking the derivative of vectors and dual vectors, and I have to use the covariant one. Okay? So let's do that. Okay. Okay, so yeah, so I'm gonna in the process of doing this, I'm gonna multiply by m, And in multiplying by m, I can take that term and turn it into a formula. Okay? So I'm going to get p nu. And then I'm going to take the derivative of the k mu first, so I'll get the p mu out, del nu k mu. And then taking the derivative on the p mu, we'll have k mu, p nu, del nu, p mu. Okay? All I've done is multiply by a mass to make this into a four momentum, which I can do because the whole equation is equal to 0. All right? And then I just distributed the derivative with the product rule, the Leibniz rule. Okay? Now, something curious is happening. Man, this is going to be a hard day. I feel like I'm in Vegas. Madison. Madison. One of those two terms is 0. Which one do you think it is? And don't guess because I'm going to follow up with why.
What?
Don't guess because I'm going to follow up with why.
Yeah, I think
Look at your notes. I wrote down something earlier in this lecture. I said this thing is equal to 0, and it appears in that equation.
Are you talking about the symmetric, anti-symmetric?
No, that's a good guess, but that's not being applied yet. You got phone a friends behind you if you want to ring in a
Yeah,
thing.
go for it. The second term is 0. It's because of metric compatibility.
This term is 0 because of metric compatibility.
Is that not right?
It's the geodesic equation. The geodesic equation I wrote was that this was equal to 0. I took the geodesic equation and I multiplied the two dx's by m to make them momenta. All right? So that's 0 because of the geodesic equation. Now I'm going to keep you on the line, Madison, because I'm going to ask you the next question. Okay? All right, so this term goes away. Everybody good? And now we can look at the first term. And I can rewrite this in a nice way. I can say p nu, p mu. Now this guy right here is arbitrary in terms of its index interchange. You can kind of think of this as a matrix that has no particular symmetry. But I can always take a matrix with no particular symmetry and I can write it as the symmetric combination plus the anti-symmetric combination. Okay, how many of you have seen that before? Let's run through it. Let's take a 2 by 2 matrix, A, B, C, D. That has no symmetry. It's not symmetric, it's not anti-symmetric. Okay? I can write that as 1/2 the symmetrized version, which is what I get if I take the matrix and I add its transpose, thank you. So if I add the transpose to this thing, then I get A, I get 2A, oh god, I'm never going to be able to do this in my head, B plus C, 2D, plus 1/2 the anti-symmetric combination, which is what I get if I take the matrix and I subtract its transpose. So that's going to be 0, B minus C, C minus B. Okay? Now let's just look at this for a second and ask, does this give us back the original thing? So this element gives me 2A plus 0 is 2A. I divide by 2, I get A. This guy is going to give me B plus C plus B minus C. That's just 2B divided by 2 gives me back B. Okay? So you can see that if you add these two matrices together, you get this one. But this matrix is symmetric. Everybody see that? This matrix is anti-symmetric. Everybody see that? Good. So we can always take a matrix and split it up into an anti-symmetric and a symmetric form. Symmetric is with the round parentheses, and anti-symmetrization means the rectangular ones or the square ones. Okay, Madison. One of these two terms is 0. Which one? It's what you wanted to say earlier.
Oh, the second one, because it's something symmetric to something.
Yeah, we have p nu, p mu, which is symmetric if I interchange nu and mu. And then we have an anti-symmetric combination of nu and mu. And that guy vanishes. Okay? So at the end of the day, we have the following conclusion. Again, p nu, p mu is not going to vanish. So we can say if the symmetric combination of the covariant derivative of the dual vector k lower mu, if this equals 0, then k mu p mu is a conserved quantity or a constant quantity. And what's interesting is that I am not relying on any particular coordinate system to say this. This is a tensor equation. This equation is true in any coordinate system. This equation is obviously not true in any coordinate system because if I change coordinates, the metric can change its functional dependence on various coordinates. Okay? This has a name that is rad. It's called Killing's equation. And the k-mu's that appear are called Killing vectors. So Killing vectors are in one-to-one correspondence with conserved quantities. But in turn, that's a one-to-one correspondence with symmetries of the geometry, or what we call isometries. So for every Killing vector we can find, there's a symmetry of the geometry. To find the Killing vectors, we solve this differential equation. This is a differential equation. We solve it for k mu. Okay. Of course, in order to write it down explicitly, you have to pick a coordinate system because you've got to pick a coordinate system, you've got to write down what the covariant derivative looks like with all the Christoffel stuff, and then you solve that for the vectors k mu in that particular coordinate system, okay? But then you can take that entire solution and transform it to any other coordinate system you want. Mike?
So like if you're given a problem, you automatically know that some quantities along some of the coordinates are conserved quantities. Can you just say, well, these are necessarily 0 and then work from there? Really?
That's actually exactly what you can do. You can, so for example, we can come back to what we said here, which is if the metric doesn't depend on a coordinate, then I know that the corresponding component of the momentum, the dual momentum, is constant. That lets me immediately identify a Killing vector. Okay? So you can do it that way. In general, though, and I'm going to work through some examples if I can get to it. In general, though, the power of this equation is that we can just solve this thing directly without relying on a special choice of coordinate system where the metric doesn't depend on things. So for example, we could apply this equation to this metric with this particular set of coordinates, and we will find the two conserved quantities. Even though looking at the metric, it's not obvious what they are. Okay? Now, one might ask the question, how many Killing vectors should we expect to find? Like, how many solutions to this should there be? And that is actually a very interesting discussion. Now, generally speaking, for a completely arbitrary geometry, it might be hard to anticipate how many of these to expect, But there is a very special case of geometries where we can actually expect a particular number of these things, and these define what are called maximally symmetric spaces. And as you might guess from your experience in physics thus far, when we go to actually solve equations for physical systems, we usually choose some kind of symmetry because that just makes solving the differential equations easier. Given that the equations we're going to be solving are highly coupled nonlinear partial differential equations for tensors that have 20 independent components, we're going to make use of symmetry a lot, okay, if we're going to make any headway. So maximally symmetric spaces are the situation where you kind of get to make the most use of symmetry. And so these are the spaces where we expect the most solutions to this. So in order to do the counting, recall, any manifold locally looks like what? Yeah, so if it's a Euclidean signature manifold, that means it's a spatial thing, not a space-time thing. Then it looks like Rn. If it's a Lorentzian signature manifold, which means it's a space-time, then it would look locally like Minkowski space. Okay? So what we can do is we can say, okay, locally, I have one of these two cases, and so I can ask what is the sort of symmetry of what things look like locally, and then the question just becomes, does that extend to the whole space? Okay? And the good thing is that the counting here is something you have seen before. So if we're in Euclidean space, or in Minkowski space for that matter, we know that you can undertake n independent translations. You know, if you're at R3, you can move along X, you can move along Y, and you can move along Z, and nothing changes. You can always translate along the independent coordinates. And then you have 1/2 n times n minus 1 rotations or Lorentz transformations. Okay, if you're in a Euclidean signature space, then all you have is rotations. You just rotate. But if you're in a Lorentzian signature space, you have the Lorentz set of transformations, which includes rotations for the spatial directions and then boosts for the space-time. Okay? Where does this thing come from? Does anybody remember? Say it again? What did you say?
I don't know, we've seen that in quantum.
You've seen it in quantum. What does this quantity count?
Isn't it the number of planes that you can rotate in?
Yeah, it's the number of planes. It's the number of independent planes in, or it's the number of coordinate planes in either of these cases. So I mean, think about it. If you're in 3 dimensions, how many planes are there? Or how many orthogonal planes are there?
3.
There are 3. There are 3. I'm not tricking you. And so if I plug 3 in here, I get 3. Okay. If I'm in 4 dimensions, how many independent planes are there?
6.
Well, here it might be harder to count, but just depend on this. There's 6. But remember, there are 6 Lorentz transformations in space-time. There's 3 rotations and 3 boosts. Okay? So that's the form of that 1/2 n times n minus 1. So altogether, these form the Euclidean or Poincare, just to give them names, but that's not that important. In total, though, we have n plus 1/2 n times n minus 1. Fortunately, I have it written down, but I'm going to make Dylan. Dylan, what does that give you?
Like, you want me to simplify that?
Yeah. I know, man, I start sweating. It's like I could do like abstract differential geometry, but when I got to add, man, I'm like, God, I'm going to get this wrong and I'm going to look like an idiot. So I'm going to let you look like an idiot. Don't worry about it. I'll save you. It's 1/2 n times n plus 1. Okay. Let's just do a quick check. If n is 4, what is this, Dylan? I'll give you an easy one. If n is 4, what is this?
It's a 10.
It's 10. But in 4 dimensions, we have 6 Lorentz transformations and 4 space-time translations. So that's what we would expect. Okay? So the short answer is that in n dimensions, this is the most number of killing vectors you would expect to find. Okay? Because locally, the space is as symmetric as you could possibly ask for it to be, and this is the most there is locally. This is not guaranteed to be the number of killing vectors, though, because the entire space might not be as symmetric as these things are. Okay? If, however, the whole space has as many killing vectors as either of these, then that space is, by definition, a maximally symmetric space. Okay? Now, you might think that to have a maximally symmetric space, you have to have one of these two things. Right? Okay, first of all, if the space you're dealing with is Rn or Mn, it is maximally symmetric because the local symmetries look just like the symmetries for the whole space. But what I'm going to argue to you is that you can have spaces which have as much symmetry as these, but are not these. Let me give you an example. So from your homework, you are very comfortable with the following space. Okay, so the surface of a sphere. I'm going to argue that the surface of the sphere is a maximally symmetric space. So, first of all, if I embed the sphere in 3 dimensions, so if I let it sit in R3, okay, so the sphere is S2, but if I let it sit in R3, then one of the things we know that's special about a sphere is I can rotate it around and nothing changes. That's what we call spherical symmetry, right? Well, just think about it. How many independent rotations of this sphere are there? There are 3. I can rotate in the xz plane, I can rotate in the yz plane, and I can rotate in the xy plane. Okay? Well, now, what is n for the sphere? It's 2. It's a 2-dimensional space. So what is 1/2 n times n plus 1 for a sphere? Gabriel, you looked at me, man. It's 3. So if the sphere is 2-dimensional and the sphere has 3 symmetries, then the sphere is maximally symmetric. But I just told you what those 3 symmetries were. Now that might seem weird because you might come over here and go, but wait a minute. You said translations and rotations, and now you're a liar. But let's think about it. Locally, we can give this that interpretation. So let's, for example, go where we love to go, the North Pole. We don't have to go to the North Pole, but let's just go to the North Pole. If you go to the North Pole and you stay very close to the North Pole, what does a rotation in the ZX plane look like? Well, no, you stay in the neighborhood of North Pole. You don't stay right at the rotation. It looks like a rotation. So, at the North Pole, this is a rotation, okay? What does a rotation in the YZ plane look like? So if I rotate in this plane, starting at the North Pole, what does that look like I'm doing? It looks like I'm translating away from the North Pole. And then this would be a translation in X. Which is exactly what I promised you. You have 2 translations, and 1 rotation. Okay? Now, maximally symmetric spaces are incredibly important for a variety of reasons. One of the reasons why maximally symmetric spaces are important is that so for maximally symmetric spaces, if we know the Ramon curvature tensor at any point, if we know the value of the Ramon curvature tensor at any point, it has to have the same value at any other point in the space. Because you're always going to have symmetry under these translations. I can literally move to a different part in the space and things have to look identical. But that means the curvature tensor has to be the same. So r mu nu alpha lambda of x mu is just a constant. Okay? It gets even better though. Turns out for maximally symmetric spaces, there is a really quick cheat to calculate the Ramon curvature tensor. At least the Ramon curvature tensor with lower indices. I can calculate that for maximally symmetric space in terms of an expression that looks like this. Does that look familiar?
Yes.
Where'd you see that? Yeah, you just worked with this expression on your previous homework. You applied this expression to what space?
Torus. Space. Torus.
Donut. Like it's
What space did you apply this to?
S2.
Yeah, you applied it to S2. Or was it S3? Was it S3? Okay, it was S3. But you applied it to S3. You applied it to a 3-sphere. Okay? A 3-sphere is an example of a maximally symmetric space. You demonstrate, well, you were supposed to demonstrate in your homework that this expression was satisfied for a 3-sphere. Okay? All right, so you can also, if you remember from our discussion of this curvature tensor with all lower indices, we expressed some symmetries. For example, we said if you interchange lambda and rho, this should be antisymmetric. Well, if I look over here, if I interchange lambda and rho, it's antisymmetric. And similarly, if I interchange mu and nu, this is antisymmetric, this is antisymmetric, and if I interchange lambda and rho with mu and nu in total, then it should be symmetric. Okay? So the symmetries that we talked about for this guy are exactly exhibited by the right-hand side expression. Okay? Now, I'm just going to finish with a list of some maximally symmetric spaces. I was going to do an example of solving Geodesic Equation, but I'm not going to keep you late. So just a catalog of maximally symmetric spaces. And we can break these up into Euclidean, signature, and Lorentzian signature. Remember, when I say Euclidean signature, all I mean is a space. There's no time in it. Lorentzian signature means a space-time. So at least one dimension, and preferably no more, is time-like. Okay? Now, what I can do, based on this expression, if you think about it, is I can break all of these maximally symmetric spaces up into 3 categories based on R, the Ricci scalar. I can break them up into solutions where R is equal to 0, where R is greater than 0, and when R is less than 0. Okay? For Euclidean spaces, this is of course Rn, just Euclidean space. Sorry, for Euclidean signature spaces, of course, Euclidean space is a Euclidean signature space with zero curvature that's maximally symmetric. It turns out that tori, n-dimensional tori, are as well. If the Ricci scalar is positive, then I'm dealing with spheres. Spheres are maximally symmetric Euclidean signature spaces with constant positive curvature. If the Ricci scalar is negative, then I'm looking at a n-dimensional space that's maximally symmetric. It's a space with constant negative curvature, and these are what are called the hyperbolic spaces. Go ahead.
I was gonna ask, could you consider the inside of the sphere? Like,
That's not a manifold. Well, you mean the interior without the sphere itself?
yeah, like, we have the surface of the sphere on the outside. That's what we've always talked about, I guess, on the inside, but I guess it doesn't.
Well, the inside is R3.
Yeah.
It's a region of R3, which is this guy. Okay. For the Lorentzian signature case, of course, as you might expect, Minkowski space itself. We can take Minkowski space and we can tensor it with tori, and those are still going to be maximally symmetric. The interesting solutions are these two, though. If you're in a space-time that is maximally symmetric and has positive constant curvature, then you are working with what is called n-dimensional de Sitter space. And if you're working with a space of negative curvature with a Lorentzian signature, then you're talking about what's called anti-de Sitter space. Anti-de Sitter space is a space which has gotten a very, very prominent role in theoretical physics, because one of the most important results that have come out of string theory, which is not a string theory result at all, it just came from string theory, is a correspondence between gravity and anti-de Sitter space and non-gravitational quantum theories on the boundary of anti-de Sitter space. So people who do research in sort of fundamental physics play in anti-de Sitter space a lot. At the end of the semester, when we study cosmology, we're going to come back to this question of what is the geometry of our universe? And that is, of course, going to be a space with either positive or negative curvature. And so our space-time geometry is going to be of either the form de Sitter or anti-de Sitter. But we'll answer that question when we get to cosmology at the end. That's it for today. What I'm going to do, because I'm not going to go over this next time because we've got so much to do, in the notes for today, I'm going to solve Killing's equation. Okay, I'm going to actually solve this differential equation for the case of the two-sphere. Okay, so have a look at this derivation. If you have any questions, bring those to me during office hours, because I'm not going to go over this during the lecture. Yes, it is.